Someone responded to my video on hurricanes, atolls and coral, very politely questioning whether total submergence beneath the waves is really not a major problem facing atolls. He cited a news report from Al Jazeera about a small group of islands at Cuna Yala off the coast of Panama, which are indeed being swamped by rising sea levels. So I took a look.
The Cuna tribe understand struggle. They survived pirates and Spanish conquistadors, a U.S. invasion, and Panamanian politicians. Their latest battle, global warming.
I'm always ready to accept that I got something wrong and correct it. But first, let's see what Al Jazeera is claiming.
This area where I'm standing, and actually within a 30-meter radius, used to be completely above the water.
Whoa, hold the tape. Now, when I saw this, I realized straight away that either we're dealing with faulty memories about where the sea level used to be, or this sea level rise is being caused by something other than global warming. If Monica Villamizar had been a science reporter, perhaps she would have questioned it too, because global warming has caused an average sea level rise of a few centimeters within living memory. Granted, it's uneven, and the Western Caribbean may be getting more than the average, but surely not enough to take the coastal water from ankle level to crotch level. So I looked for more information, and it turned out Reuters had done a story on Cuna Yala 5 months earlier, saying pretty much the same thing. That's probably where Al Jazeera got the inspiration to do its story. Except Reuters blamed a lot of the inundation on the damage to the coral reef, as well as global warming. Now, the destruction of coral would account for storm surges and coastal erosion, sure, but not permanent sea level rise to the extent the islanders described to Al Jazeera. There was just one other possibility. The sea wasn't rising, the entire crust on which the islands sat was sinking. The Caribbean is well known as an area of complex interacting tectonic blocks, so I checked to see if there are any tectonic plate movements that might be causing that part of Panama to subside. And it couldn't be more obvious. The Cuna Yala Islands lie just south of a subduction zone, which means the crust they sit on is being dragged downwards as the Caribbean plate to the north subducts underneath. So then I went in search of papers that confirmed subduction under the Cuna Yala region, and here it is. The results indicate such large variations in both direction and rate of secular movement as to rule out changes in volume of ocean water as being more than a subordinate factor. The only satisfactory explanation is that the land level beneath the tide gauges is rising in some places and sinking in others.
Their latest battle, global warming.
Now, I don't want to be too hard on the reporter, because science is clearly not her beat. The fault really lies with Al Jazeera and all the other networks that assume reporting on a story on the environment means assigning your most poetic journalist to do a touchy-feely human interest piece instead of looking at it first and foremost as a science story. Before the conspiracy theorists start saying, "Ha, told you so," this works both ways. I still remember a Paul Harvey report from 20 years ago where he refused to accept the fact that sea levels were rising because, he said, the sea level is rising in the south of England but falling in the north of Scotland. So it must all be bunkum.
And now, the rest of the story.
It's not the sea rising and falling, but a case of the land rising and falling. It's known as glacial rebound. There was so much ice weighing down the north of Britain 20,000 years ago that when the ice melted, the crust began a process of what's called isostatic uplift. And it's still rising today, pushing down poor old England as it does so. Sounds a great cheering from the Scots. But when reporters fail to understand this and confuse tectonic subsidence with climate change, that just muddies the waters even further. Because when people like me point out that they're wrong, there's a danger that conspiracy theorists will seize on that as a claim that none of the science can be trusted. But remember, what you see in the media is not necessarily what's in the scientific literature. Most media reports I've seen do reflect the scientific literature quite well. The ones that fail are the ones that don't use scientific research as a source. So if you want to know if a media report can be trusted, listen out or read carefully to see where the information comes from. It has to be research published in a respected peer-reviewed journal. Not a quote from someone who doesn't do any research in that field, not common sense or something that seems obvious to the reporter, not a piece of information from the internet or a clever bloke down the pub that fits into an editorial position, not the interpretation of an editor who failed high school science, not by looking out of the window and assuming that daffodils in January must be the result of global warming. In the next video, we'll see a classic example.
You'll remember from the lesson on Earth's formation, seafloor sediments are extremely important records of Earth's past climate. How? The species of diatoms, coccolithophores, radiolarian, and foraminifera will change as seawater temperatures change. In addition, the type of sediment that is deposited will change. Increased glacial activity on land during an ice age will bring more sediment to the margins, and in areas closer to the poles, these sediments will consist of large, angular, immature material carried by glaciers, and then sea ice. In the mid-latitudes, where glacial ice was present only in the mountains, rivers have a higher amount of water and sediment. Sea level drops as water is trapped on land in glaciers. The new coastline moves out toward the edge of the continental shelf, or break. The area exposed can be covered by huge amounts of delta sediments and sands. What's the deepest part of the oceans that can be exposed during an ice age? The continental break. Do you remember how deep the depth is at the break mentioned in a previous lecture? 125 meters, or about 375 feet. That's the deepest sea level will drop during an ice age. What's the average depth of the oceans? 4,000 meters. So most of the ocean is still covered. Since the Earth has experienced multiple episodes of ice ages and interglacials during the past 1.6 million years of the Pleistocene, what story do our shelf sediments record? Let's imagine we take a research cruise to the outer shelf near the break and drill through the layers of sediment that have collected. What will we find? What kind of sediment is collecting there today? Assuming it's a wide shelf, we would expect mostly muds that far offshore, maybe some fine sands. What's under them? The sediment that collected during the last ice age when that spot was the beach. What kinds of sediment collect along a beach? Gravels and sands. So we should see alternating sequences of sediments representing different levels of the ocean. In fact, if we wanted to study fishing villages of earlier cultures that lived 15,000 years ago during the last ice age, we would have to go to the edge of the shelf and drill through many layers of sediment that have deposited since, bearing those records. What's the highest sea level could be if we melted all the current glaciers, a direction the planet is currently heading, as it has many times in the past 1.6 million years of glacials and interglacials? 70 meters above current sea level. Are there other ways to cause sea level to change besides an ice age? What happens if we simply cool water without producing glaciers? What happens to water as we cool it? Or the reverse, what happens to water as we warm it? To answer that, let's watch what happens to a marshmallow in a microwave. This peep is cold, compact, and well preserved. Want to see what it looks like after we heat it? What would we expect? The molecules of marshmallow will pick up energy, moving faster and spreading themselves further and further apart, expanding. The marshmallow should grow. And here's the result. So warming up water should cause it to expand, much like what happens during convection. The expanded warmer water rises up because it's less dense, while the colder, denser material sinks to get heated up itself. In this case, we warm up all the oceans, so all of it expands. Sea level would rise, and if the water then cools, it would contract, sea level would drop. One more way to change sea level is to change the size of the ocean basins. If we make the bathtub bigger, so to speak, the water that fills it will have more room. Sea level will drop. The reverse, shrinking the bathtub, would make sea level rise. As seafloor spreading rates change in the world's oceans, so too will the size of the oceans change, and correspondingly sea level. What's the lowest sea level has been in the past few million years of Earth's history as a result of cooling oceans, ice ages, or larger ocean basins? About 130 meters below its present position. What's the highest sea level has been? about 170 meters, and that was during the Cretaceous over 100 million years ago, when average surface temperatures were 10 degrees Celsius warmer than they are today. Remember that the average elevation of the land is 800 meters, so 170 meters wouldn't cover much. However, it would cover about 85% of the world's population, as that's where the majority of our population centers and associated infrastructure are located. This fact is probably one of the most important you will learn in this class this semester. Sea level is rising and will have a huge financial impact on the future of human civilization. An intelligent and sustainable plan for future development should include a good understanding of this regular and natural process of sea level fluctuation. Temporary and transportable structures are logical for building within 100 meters of sea level. Permanent structures will require constant financial input to maintain in the face of rising sea level. Pause now.
Hi, I'm Dr. Megan Saunders. By 2100, the sea level is predicted to be almost a meter higher than it is today. And this will have some really serious consequences for people who live in the coastal zone. Not only that, it will also change the distribution of coastal habitats, like mangrove forests, as shown behind me, and coral reefs and seagrasses, because these things live very close to the sea surface. These habitats also support high biodiversity and the livelihoods of hundreds of millions of people worldwide. So we're really concerned as to whether sea level rise will have negative impacts in these habitats. At the University of Queensland, we are developing computer models, which examine the response of coastal habitats to rising seas. I spoke with Professor Stuart Finn, who's a chief investigator on the Australia Sea Level Rise project.
So the objective of the Australian Sea Level Rise project is to combine study of biological and physical changes in the environment to understand how sea level rise will affect the biology of the coast and marine areas, as well as physical changes, and to take that information and put it in a form that can be used to help with social and economic planning to help society adapt to sea level rise and change in the future. The development of policy and guidelines for sustainable use of the environment requires knowledge of how the environment changes, so understanding biology and physical parts of the environment, and those people then work with social and economic scientists to develop the policy for local, state and national governments.
One of the projects we're working on looks at the effect of sea level rise on seagrass, which form vast undersea meadows. For this project, we first needed to collect information on where seagrass occurs in our study sites, which were various places in Queensland. To do this, we use remote sensing imagery, images taken from satellites. And we inform those images using field data, which we collect by snorkeling or scuba diving in the study sites. We also needed a digital elevation model. This is basically a map showing the water depth and height of the land in every location in our study area. To make these, we use satellite imagery from remote sensing, as well as information from geographic positioning systems and nautical charts. We also need some information on the environmental conditions where the seagrass is living, such as the water clarity and wave height. Once we have all of these data sets together, we can then examine the relationships between where seagrass occurs and doesn't, and the environment in those places. We can then simulate the sea level rising and repredict where we expect the environment to be suitable for seagrass in the future. This gives us a detailed map of a predicted future habitat of seagrass.
The main findings of the study is that coastal habitats will change quite significantly and we will lose large portions of them, specifically seagrass, because it can't grow where the water becomes too deep, and then it can't colonise or re-establish in areas that are inundated because there's existing infrastructure and buildings there.
Dr. Mirena Mills is a conservation planner, and she uses the results of habitat distribution models for seagrass, mangroves, and coral reefs in her research.
So my research is about understanding how coastal ecosystems will migrate in the future and where the best places for development will be in the future, so we can reconcile both ecosystem or conservation goals and development goals with rising seas.
We can't stop the sea level from rising, but what our research has shown is that we can use the best scientific information to inform management plans for our coastal zones. And this can help ensure the best possible future for both human beings and the coastal habitats that we rely on.